Okay, Trig, I'm home with a sick kiddo today. She's sleeping, so if you can hear snoring, that's what that is. We are on the second half, the graphing side of log functions 3.3. Here's the homework assignment for that. If you didn't get that written down from yesterday, there is that. We are on like example 7? Example 7, yeah. Talking about graphs, okay? So up here we were doing like shortcuts of logs and exponentials and converting between. Now we're going to talk about the graphs of log functions. Okay, so if you look at this left side one, the blue, this is what an exponential function looks like. And I kind of talked a little bit about this yesterday, I guess. Those exponential functions will always go through 1 unless we move them up, down, left, right. So like this would be an example of like 3 to the x power, right? So unless I do like plus 2 on the end of it where I move him up to, he's 3 to the x power is always going to go through 1, or 7 to the x power. They'll always go through 1, and they will have a horizontal asymptote here at 0, okay? Now, we know that log functions and exponential functions are inverses. So if this is an exponential function, inverses are flipped across that line y equals x, and this is the equivalent log function. So this would be like log base 3, and he will go through 1 on the x-axis here instead, and he will have a vertical asymptote. He won't have a horizontal asymptote, he'll have a vertical one, because he's flipped over top of that inverted line. Okay, now, it's the same way with, like, if this instead was 5 to the x power. The inverse of that would be log base 5. They will still go through 1 on the x and y axis. It's just that, like, 5 to the x power will look more like he'll be narrower on the exponential function, which means he'll be like flatter for a log function. 5 to the x power is going to increase faster than what 3 to the x power will. So 3 will look more of a C, 5 will look more of an L. Okay, and the larger your base is, the more that will happen. It'll look more, I don't know, upright, I guess. So that's how that works, okay? Over here, this is where your base is a number that's less than 1. So like this is an exponential decay function. Okay, so that would be like 1/2 to the x power. He goes down and he still has a horizontal asymptote, and still intersects at 1, but he's the opposite direction. Instead of going uphill like this, he'll go downhill. Log will be the same way. So log base 1/2 will still cross through 1, but he'll go this direction. Still having a vertical asymptote, but instead of going this way, he'll go the other way, okay? So this is for decay functions, or decay, I don't know why, decay functions, or for bases that are numbers that are less than 1. Here's for like growth functions or bases that are greater than 1, okay? So graphing functions, here we go. Graph the function log base 2 of x. We're just going to do a rough sketch, and I usually start with the exponential function. So 2 to the x power is his inverse, and I'm just going to plot just a couple dots on here. Oh, that's not straight. We know that 2 to the x power is going to go through 1, but another dot that I could put on there, like, this is the point 0, 1, because if I plug 0 into my x, 2 to the 0 power is 1, right? But if I plug 1 in, 2 to the first power is 2. So I have the point 1, 2, and that gives me a second point on my graph, so I can see kind of like how fast that thing is increasing, okay? So it gives you kind of your second dot on there. Now, if I switch gears and I want to graph log base 2, I know that if this point is 0, 1, and this point is 1, 2, and I invert those, I just switch the coordinate points. So I have the point 1, 0, which is this one, and I have the point 2, 1, which is this guy. And he is going to go like this, okay, where the vertical asymptote is the y-axis. So if you get just 2 points on your graph, just flip them around, and that will be what the inverse is, or what the log function is. So that's what he will look like. Graph the functions. There you go. The blue one is the log. The black one is the exponential function. Okay, I'm going to do the same thing here. This one has a base of 1/4. So I think in terms of like the exponential function is 1/4 to the x power. Okay, that's going to be a decay function. So I still know that if I plug 0 in, I get 1. 1/4 to the 0 power is 1, so I still have that dot right there, but I know he's going to go do one of these, okay? Now, let's do this real quick. If I go, I'm going to go back negative over here. If I do 1/4 to the negative first power, okay, negative powers flip fractions, okay, this is going to be the same thing as positive 4/1 to the positive first power, right? Like I take that and I flip it, and this exponent becomes positive. So if I'm back at -1, if I plug -1 in, that is going to be 4/1 to the first power, or just 4. So 1, 2, 3, 4. He will be this point, -1, 4. Okay, so that will kind of give me the curve of what that exponential function looks like, right? I still have 0, 1 on that graph, but then if I make him a negative exponent, he'll be up at 4. So this magical dotted line of y equals x where he's inverted, if I flip those coordinate points around, I now have 1, 0, which is this guy, and I have 4, 2, 3, 4, -1. And he will look, he'll have a vertical asymptote, but he'll look like this instead, okay? Vertical asymptote here, and he's going to look like that. Okay, so log is the green one, the exponential function is the blue, or is the black one. So I usually like to graph the exponential one first, just to get the right like points that he goes through. Okay. All right, now they're going to start talking about domain and range. We're going to do the example first, and then we'll discuss domain and range. So I'll come back to that box, but you guys know how to find domain and range from a graph. So if you want to read through that box, you can. Let's go down here. This is log base 2 of this junk, okay? Let's just talk about what like log base 2 of x is, because we just kind of graphed him. Did we graph him up above? Yeah, log base 2 of x. We just graphed him up above. Okay, log base 2 of x, we said went through this point, but then if I go over 2, he's at 1, right? So he looks like, no, that's not right. I went on the wrong spot, right here. This is what log base 2 of x is, okay? And he has a vertical asymptote right here at 0, okay? This vertical asymptote is at x equals 0. So that's where my VA is located. If you want specifics, x equals 0 is the equation for your VA, because we're going to have to find the new VA here in a second, okay? Then let's just talk. So we have log base 2 of x graphed. Let's figure out what the plus 3 is doing. Oh, now I have a helper. Okay. You can help? Okay. We're done with nap. We're done with our nap. Okay, so we've got that plus 3, and the plus 3 is going to move him to the left 3, and the minus 2 is going to move him down 2, okay? Remember that here the minus actually means down, but here plus means left. So here it's kind of the opposite, but when it's outside parentheses, it's like the same as the way that you think, okay? So left 3, down 2. What I'm going to do is I'm going to take this vertical asymptote. I'm going to move him left 3, 1, 2, 3. Moving him down 2 doesn't move the vertical asymptote, right? Because he goes up and down forever. So left 3, down 2, that's going to move my vertical asymptote there, okay? I'm going to take this dot, move him left 3, and down 2. And there's where that spot is. If you want to move this guy left 3, down 2, left 1, 2, 3, down 1, 2, he'll be right here. So now my log function will be like this, okay? So the VA now is at x equals -3, okay? Identify the vertical asymptote and write the domain and range. So the VA, x equals -3. I'll show you how to cheat there here in a second to find that VA. And then domain and range. Domain, range. Okay. Oh, just domain. Just domain. Okay. The range is going to be all reals because he's going to go up and down forever. Okay. But domain, he's only on the left side of this VA. So for domain, the x's are greater than -3. That's not interval notation yet, though, okay? He's not touching -3, so he's not equal to -3. If you write interval notation, he'll go from -3 to infinity paren, because he's not touching -3. So this is the VA, this is the domain. They go hand in hand with each other because that's like kind of how it works, okay? Now, to cheat. So that's the answer. To cheat, your VA will always be located where you set this inside guy equal to 0. So whatever's on the inside, don't include the -2. But the parentheses stuff was x plus 3. If I set him equal to 0 and subtract the 3 over, I have my VA. My VA is there. There he is, okay? So that's how that works, just so you know, okay? All right, let's go down here and let's talk about these guys and the graphs of those guys, right? The domain. So they don't actually want us to graph, but I'm going to do a little rough sketch. We have log base 2 of this thing. Okay, so if I'm trying to locate domain, I need to know va first. Okay, so I showed you the little trick, and the little trick was saying 2x plus 4. If I set him equal to 0, that's the va. All right, I'm going to subtract the 4. Some of you guys can do this in your head. 2x equals negative 4. X will be negative 2. That's where my va will be located. All right, now, the book says to do this instead. Okay, here's where my va is, negative 2, like this. That's where my va is located, okay? The graph of my function is probably going to do like something like this, but here's the way that the book tells you to do it, okay? They kind of go in the same route, and they say, okay, this thing right here, he will tell me the va if I set him equal to 0, but also, we talked about this yesterday, when you're taking a log, you cannot take a log of a negative number, right? Like if I try to say log of negative 3, I think I told you to do yesterday, and it comes up with domain error in your calculator. You can't do that because the graph doesn't go negative. You don't have negative numbers to plug in. So here's what the book tells you to do. They say you can find the domain by saying, I know that this stuff, 2x plus 4, has to be a number that's greater than 0. Right? Because I can't plug a negative number in this spot and take log of it, right? So if I'm wanting to do domain, let's just set him greater than 0 instead of setting him equal to 0 to find the va. If I do that, I will end up with x is greater than negative 2. This is my domain. If you want to put that in interval notation, you're going from negative 2 to infinity, and that is that, okay? So, little trick, set him equal to 0 to find the va, but you can set him greater than 0 to find the domain because that number has to be a number bigger than 0 in order to plug him in. Okay, let's use that same concept here. I know that 5 minus x, that I'm taking a log of. I'm taking ln of 5 minus x. So if I'm trying to find just the domain, I'm going to say 5 minus x has to be a number that's bigger than 0. Otherwise, I can't take log of it. It won't work. Okay, so then if I solve, I'm going to subtract the 5x. Some of you guys might add the x over, whatever. Negative x is greater than negative 5. Cool. Divide by negative 1, and you get x is, we have to flip the sign because we divided by a negative. So x is less than 5. This is my domain, okay? And so he is going, if x is less than 5, he's going from negative infinity to 5, bracket, or paren. That's my stuff, okay? If you're interested to know, like, what this thing looks like, okay, he actually, at 5, 1, 2, 3, 4, 5, that's where my vertical asymptote is, but because this negative is here in front of the x, this flips him like over the x-axis and then moves him to the right, so he is actually doing one of these things. That's not in the right spot, but anyway, you get the idea. That's why he's going from negative infinity to 5 is because he's flipped not over x, over the y-axis, okay? So he's flipped over the y-axis and then he's moved over for my va, okay? That's how that works, all right? C. This one's a little bit more weird because we have a quadratic function. So we've got x squared minus 9. He has to be greater than 0. Whatever that is has to be greater than 0. Okay. So what I'm going to do is I'm going to solve this thing. You can either separate him as a difference of squares, or I'm just going to add the 9 over. So x squared has to be greater than 9. I'm going to take the square root. But the square root of 9 is 3. So I've got this thing going on. And if you remember back from when we were solving quadratic inequalities, when you get two answers, you have to kind of like look at it on a number line and verify that you don't have weird symbols going on. Because like when you get two answers over here, this symbol might not be in the correct direction, if that makes sense, okay? So negative 3, positive 3, I'm going to test some points. I'm going to test negative 4, I'm going to test 0, I'm going to test positive 4, okay? So I want to know what numbers I can have and what I can't have. If I plug negative 4 into, like, let's say this guy here, negative 4 squared minus 9. Negative 4 squared is 16. 16 minus 9 is 7. I want that number to be bigger than 0 because I have to be able to take log of it, and that works, okay? If I plug 0 in, 0 squared minus 9 is negative 9. I can't take log of a negative 9, so that's not going to work. I don't have numbers there, okay? If I plug positive 4 in, 4 squared minus 9, that's going to give me that 7 again, and I can take log of 7 because that's a number bigger than 0, so I can do that, okay? So what I have going on here for domain, if you want to write it in interval notation, we're going from negative infinity to negative 3. Those numbers I'm allowed to plug into here because they work, right? unioned with 3 to infinity. Those are the only numbers that I'm allowed to plug into here because that will give me positive numbers. Negative numbers, I'll get negative numbers if I plug in numbers between there, right? Like I don't want that to happen, okay? What this looks like when you graph it, just so you know, is like this. I have 2 vertical asymptotes, one at -3, okay, and one at +3. And this is just what happens with a quadratic function. So you have kind of like 2 logs going on. You'll have, what happened? You'll have one log going this direction, one log going this direction. So they're kind of like, there's 2 of them at the same time, and they're symmetric with each other. So mine don't look symmetric, but nothing going on over here. But I have 2 log functions on one on the left and one on the right. Okay, and that's just what happens with an x squared inside of a log. Okay, you'll just have 2 pieces, kind of. Okay. All right, last thing is the story problem, okay? But before we get to that, here are some applications of when logs are used. So like measuring pH for, I don't know, in science class or whatever, the pH scale goes from 0 to 14. So like 0 to 7, I think, is acids, and then 7 to 14 is bases, something like that, whatever. That stuff is measured in concentrations of hydrogen ions, which is a log function. Okay, like they use bases of 10 to note that, like the intensity of the hydrogen ion concentration or whatever. Okay, so that's somewhere where logs are used. We're going to do this example, example 2, measuring wave energy from an earthquake. So when they say like on the Richter scale, it was we just had an earthquake a while back, and I don't know what they measured it on a Richter scale. Maybe it was like at a 3 or something. I think if it's like less than 2, you don't even feel it. Okay, but it goes from, like, the Richter scale goes from 0 to, I don't know, I think it goes above 10, but 10 is like really bad. So that, though, measures intensity. So it's not to say that like a Richter scale, if you have a Richter scale that measures an earthquake at a 6 and then a Richter scale that measures an earthquake at a 3, it doesn't mean that this is 3 times as bad as what, like the 6 isn't twice as bad as what the 3 is. It's actually, this is actually 10 to the 6th power, and this is 10 to the 3rd power, right? So if I divide those, 10 to the 6th divided by 10 to the 3rd is 10 to the 3rd. It is 1 with 3 zeros. It is 1,000 times more intense for a Richter scale of a 6 than a Richter scale of a 3. That's how that works. It's not like this is double this one. It's 1,000 times worse, okay? And that's why we use log functions and exponential functions to indicate that, because it's not just looking at these numbers, it's looking at like 10 to that power, okay? And then also like loudness of sound is measured in watts, and those are measured like 10 to whatever power, so we use logs to represent those as well, okay? So here's our intensity of earthquake function. The intensity I of an earthquake is measured by a seismograph, a device that measures amplitude of shock waves. I0, I sub 0, or they call it I naught, is the minimum reference for intensity of a 0 level earthquake. So that's no earthquake at all, against the intensity of other earthquakes that they can compare, okay? So this is the function that we use to identify what the magnitude is, okay? So here we go. In part A. A and B are kind of like too easy, but you get bogged down with the notation of it. So here we go. Determine the magnitude of an earthquake that devastated Haiti on January 12th of 2010 if the intensity was approximately 10 to the 7th times what I naught is, okay? So that is what I is, okay? Here's how we're going to write this, okay? I naught is down below here in the formula, but the intensity of that earthquake was 10 to the 7.0 power times what I naught was, right? Like that's what that was. The intensity of this earthquake was 10 to the 7th times the initial like earthquake at 0, right? So the way that this works is we can cancel those out, and this is just saying what is log of 10 to the 7.0 power, okay? And we talked about from yesterday how if a log doesn't have a base, its base is 10, and then these two will cancel out. So the magnitude of that earthquake is a 7.0, right? Like that just kind of makes sense You know, I just kind of told you before that a Richter scale of a 10 is 10 to the 6th, right? So like that exponent will tell me what the magnitude is. Okay, B, if you want to take a guess, the intensity was 10.5, or excuse me, 10 to the 5.8 times what the initial is. So I'm going to guess that the magnitude is 5.8, but here's why. Log of, if my intensity is 10 to the 5.8 times what the initial is, divided by the initial, I can cancel those out. Log of 10 to the 5.8 power, those can cancel out, and so I just get a magnitude of 5.8, okay? Now part C asks something just a touch different. I'll use a different color. How many times more intense, this goes back to the example that I had up here, how many times more intense was this earthquake than this one, right? So one of them was a 7, one of them is a 5.8, and you're like, do I just subtract those numbers, or do I just divide those numbers, or what do I do, right? Okay, so the first one was 10 to the 7.0, and I want to find how many times intense it was, so I'm going to divide those. 10 to the 5.8 power, okay? Now, when you're dividing those, I'm going to subtract those exponents, like x to the 5th over x to the 2nd power, right? I subtract those, and that's x to the 3rd, right? So I'm subtracting these exponents up here, and if I do that, I get 10 to the 1.2 power. If I take 7.0 minus 5.8, that's 1.2 power. So it's not that it's 1.2 times more intense. That means it's 10 to the 1.2 power. If you type 10 to the 1.2 power in your calculator, you get something like close to 16. So that means a 7.0 on a Richter scale is 16 times more intense than a 5.8. Not 1.2 times more intense, 10 to the 1.2, which is 16 times more intense, okay? So hopefully that made sense. That's why we use 10 to that power to do intensity, because like that's how it's reflected on the Richter scale, okay? 16 times more intense, not 1.2. Okay. All right. So that was a long kind of example, but there you go. That's it. Here is the homework assignment again, if you need to pause there. But go ahead and get a start on those, and we will go over questions tomorrow. Okay.